Welcome students, welcome again to my new lecture. I am Mohammad Tanvir Ahmed, lecturer at Department of Civil Engineering, World University of Bangladesh. Mostly overall content, that means overall organic content will measure total organic carbon, that means TOC, biochemical oxygen demand, which is BOD, and chemical oxygen demand, COD. Among of them, BOD and COD are most commonly used for design and effluent specifications. In this lecture, we will give priority in BOD and COD. Oxygen demand. It is the demand of the oxygen required to oxidize the organic matter present in a wastewater sample. So we can say it is a measure of the amount of reduced organic matter in water. It relates to oxygen consumption in a river or lake as a result of a pollution discharge. As you know, oxygen consumption depends on discharge of pollution. It can be measured in several ways, such as biochemical oxygen demand, which is BOD, chemical oxygen demand, which is COD, and theoretical oxygen demand, which is TSOD. Biochemical oxygen demand, BOD. It is the amount of oxygen demanded by a wastewater sample. So we can say BOD is the measure of oxygen required for biological oxidation of organics. In another way, we can say BOD is the oxygen uptake by microorganisms during aerobic growth in wastewater sample. The standard for BOD test is 5-day incubation at 20 degrees Celsius or a 10-day incubation period. Among of them, 5-day BOD or 5-day incubation is most commonly used as it requires less time. The 5-day BOD is about 68% of the ultimate and 10-day BOD is about 90% of the ultimate. Samples requires a series of dilution to achieve suitable oxygen consumptions. Here, this is a dissolved oxygen versus time graph, and we have obtained this graph from a BOD test on a wastewater sample. The sample was diluted by a factor of 20 prior to the test. We know BOD equal to loss of oxygen in milligram per liter into dilution factor. Here, when time t is 0, that means at the starting of the test, the dissolved oxygen was 8 mg per liter. And after 5 days, the dissolved oxygen stands 1.7 mg per liter. We have taken 5 days as normally BOD is carried in a 5-day incubation period. So we can write loss of oxygen equal to 8 minus 1.7 mg per liter, which represents here 8 minus 1.7, and this 20 is the dilution factor. It is also represented here. So we get BOD equal to 126 mg per liter. Here this is BOD, that means biochemical oxygen demand, and this 5 represents that this test was carried in a 5-day incubation period. Practical concerns with BOD test. The BOD degrades only partial organic matters. The test results will be unreliable when the BOD load will be greater than 1000 mg per liter and lower than 10 mg per liter. Industrial wastewater can contain inhibitors, leading to low BOD results. Briefly, the BOD test employs a bacterial seed to catalyze the oxidation of 300 ml of full strength or diluted wastewater. The strength of the undiluted wastewater is then determined from the dilution factor and the difference between the initial DO and the final DO. So, if we take a full strength wastewater, that means the wastewater without dilution, then the BOD will be a BODT, that means a BOD after any time t, equal to DOI, that means dissolved oxygen at the initial time, minus DOF, that means dissolved oxygen after the test or final dissolved oxygen. If we take a diluted wastewater, then the BOD will be BODT equal to DOI minus DOF divided by VS minus VB, where BODT equal to biochemical oxygen demand at any time t, DOI equal to initial dissolved oxygen, DOF equal to final dissolved oxygen, Vs equal to sample volume, Vb equal to bottle volume. Usually BOD bottle ranges from 300 to 250 milliliter. This is a BOD versus time graph, and here the first portion is carbonaceous BOD and the second portion is nitrogenous BOD. So we can say carbonaceous BOD will oxidize first and then the nitrogenous BOD. Oxygen consumption at any time t, which is equivalent to BOD at any time t, can be calculated using equation BODT equal to L0 minus LT, where L0 is the BOD loading at initial or at starting, as initially the BOD is greater and after a certain time t, the BOD loading will decrease as oxidization continues, and this LT is the BOD loading after any time t. This graph represents BOD remaining versus time. Initially, the BOD remaining is high, and as time goes, the remaining BOD decreases as oxidization continues. As with time, the BOD remaining decreases, so the demand of oxygen will also decrease. This deep color bottle indicates high BOD loading, and this lighter color bottle indicates lower BOD loading. As we know, BOD loading decreases with time. So with the time, this lighter color bottle indicates lower BOD loading. Here, L0 is the ultimate BOD. LT is the amount of oxygen demand remaining after any time t. dLt by dt is the rate of change of BOD loading, which is proportional to LT. If we add a constant k, we will get dLt by dt equal to minus kLt. Negative sign uses here as rate of BOD decreases with time. If we integrate this with the boundary limit LT and N0 with the time t and 0, we will get LT equal to L0 e to the power minus kt. Again, we know L0 equal to BODT plus LT. If we replace LT equal to L0 e to the power kt in this equation, we will get BODT equal to L0 into 1 minus e to the power kt. Basically, this is the equation which we will use to calculate the remaining BOD after any time t. These are the typical values for the BOD rate constant. For raw sewage, the value of K will be 0.35 to 0.70. For well-treated sewage, it will be 0.1 to 0.25. For polluted river water, it will be 0.1 to 0.25. The value of K can also be determined in laboratory along with L0 by measuring BODT at two different times. Effects of temperature on K. The commonly used expression to determine K is Kt equal to K20 into theta to the power T minus 20. Here, K is the rate constant, T is the temperature for which temp we need to calculate the rate constant. K20 is the rate constant at 20 degrees Celsius. Then normally we will use here 0.10. Theta is a constant which is equal to 1.047. Chemical oxygen demand, which is known as COD. It is the measure of oxygen required for chemical oxidation of organics. Chemical oxidants used for oxidation of organics to carbon dioxide, H2O, and ammonia. During oxidation, dichromate is used up and remaining oxidant is measured spectrophotometrically to determine oxidant used. COD. A chemical test. The chemical oxygen demand COD of a waste is measured in terms of the amount of potassium dichromate reduced by the sample during 2 hours of reflux in a medium of boiling. THOD, theoretical oxygen demand. It is the total amount of oxygen required to completely oxidize a known compound of carbon dioxide and H2O. It is a theoretical calculation that depends on simple stoichiometric principles. It can only be calculated on compounds of known composition. That is the end of our today's lecture. Thank you everyone.